Thank you very much for having us here. Good afternoon, everyone. My name is Basel, and
I'm Isabella.
today we're going to give our talk about Myo-esthetics, low-cost prosthetics for children. Right. So, who are we as a society, and what are our aims? Why do we have you guys gathered over here? Why are we talking about this? Well, simply put, we are basically a student society, a student-based society of a much bigger community here at the University of Glasgow. We kind of represent the Handprints Enable wider community in the sense that they all come together, projects, people who come in and they donate prosthetic arms to children. It's kind of a collaborative thing that's open source. People come together and they donate these 3D printed arms. That is our main aims and goals. However, we as a society here at the University of Glasgow are based off of fundraisers and charities. So these are one of our kind of challenges that we needed to overcome. And at the end of the day, what we traditionally provide for these children is the 3D printed arms, because our target for them is because since these children are usually under the age of 10, they lack the necessary funding or needs in order to get a traditional prosthetic arm. So we 3D print them, try and make them as low cost as possible, and the way to try and minimize that such that they don't kind of crumble apart. So again, I've probably spoken too much about what we do as a society or our aims. We are kind of more focused on the research aspect of it. So as you can see here from the diagrams, our aims and goals of the traditional prosthetic arms are slightly different, because what we do is something that's called a Myoelectric prosthetic. And essentially its components, as you can see here, you've got something coming from these electrodes, a muscle or an impulse, basically. And what they do is that these electrical signals that are generated, they get translated into the microcomputer, what we call, or a microprocessor controller. They read these signals and then they send it off to the motors, which are found in the arms. And these motors essentially try and actuate or move the fingers of them. At the end of the day, the goals and the challenges are kind of similar to what was spoken about earlier in terms of cost or weight. However, this kind of project that is specific to us provides added challenges. So things such as electrical components, things such as trying to figure out the software part of it, the aspects, kind of all comes in together. But at the end of the day, we tried to make this work, as now my colleague Isabella will try and present to you the progress of the team throughout the years. Sorry, you didn't tell it.
No.
Okay. Sorry.
So how we've gotten to where we are today, this project consists of a whole team of people from various different backgrounds who have all been working on this together. The project started for the very first time over the summer in 2018, which in the end of that we got our first prototype, which it was a good stepping stone for us to continue working on, but it did have quite a few areas which we needed to continue developing upon. So some of these were the strength and range of movement of the fingers, as it wasn't quite able to grab a lot of objects. The size of the hand was quite big and bulky, and the electrical components weren't strong enough to drive the fingers as well. So throughout the summer, our design team has put a lot of effort into improving these things. And in our latest design, all of these things have been improved. The palm has been completely redesigned, looks more anatomically correct, even though we want to focus on the uniqueness of deficiencies and empower that. We found it important that it did mimic it a bit more, as well as just to get a more natural grip. The fingers have become a lot stronger and has a larger range of movement, which allows for the hand to grab a lot of different objects now as well. They designed a wrist so it makes it possible for the hand to rotate in this direction as well. For the internals of the hand, we have all of our electrical components, which have undergone quite a lot of changes this summer as well. In our first prototype, there were a lot of wires sticking out of it, and they would tend to break in very inconvenient times. So by creating a circuit board that would some of these wires internally, it made our whole system a lot more sturdy. You can see all of these things are something that we need to fit into the hand as well, so that's kind of an added challenge. But all of this makes up our current prototype that we're working on right now, which we've called the Itsy Bitsy Spider, and it's based on the names of some of the electrical components that are inside the hand and the software as well. So this is kind of the stage we're at now, and we're continuing to develop upon. But how would you actually control this hand? This is the area of the project that I've been working on for the most part of it. And so how would you write the code so that the user knows how to control the hand? It's based, as mentioned, on the electrical impulses from your muscles. And you can see an example of what that would look like on the graph. The blue shows the raw data that is picked up, and the red one is the processed data, and is what we use for our application. This signal is sent into the microcontroller, which is essentially a small computer that interprets these signals and gives an output to the motors, which then drives the fingers. In order for the user to control this, it's based on time. So for the duration that the user contracts their muscle, the fingers will continue to close and will stop once the system detects that the muscles are relaxed. Any given contraction after that will then open the hand, send the hand to default open position again. We've written the code in this way in order to try and give the users a feel for how much force they're providing so that they don't crush fragile objects. But doing it this way, we need to have a very accurate threshold so we know when the muscle is tense or relaxed. And this threshold is quite important to find accurate since it changes from person to person, and it changes from the same person from day to day or even throughout the day, just depending if your muscles are more tired. So in order to try to overcome this, we wrote a code to auto-calibrate this threshold, so it automatically detects the thresholds for the user, and this has made the whole system a lot more reliable and easier to control. We currently have 2 different grips in the program, so the hand can do a power grip or a pinch grip, and to change between these 2 grips, we have a switch on the arm, so the user can easily change between the 2.
Okay, so to try and not bore you to death with the electronics kind of things, which I was more responsible of throughout the summer and currently now within the project. As mentioned before, as part of the added challenges to the project, when we usually try and figure components out. So essentially here you can see that in the first iteration of the hand in 2018, these were the original motors, then we swapped them to the ones later in 2019. However, this was proven to be a poor choice. And basically when we try and choose these components, we kind of have to base it off on previous research from other projects and other universities. And then at the end of the day, we take that and we try and match them with the functional requirements of the user. So remember when I've mentioned before, you've got the low cost, low weight. However, we found out later on that the motors in the 2019 part was actually ones that were not able to kind of move the fingers efficiently, so we wouldn't go the full extent when trying to move these. And that proved as another challenge, and then it was a costly mistake. So definitely next time when trying to do such kind of projects, to learn from the future or try to build upon it, is to do further research and look more efficiently into that.
So where do we go from here and what have we achieved so far? So up until now, our main things that we've achieved is a design of a hand that is able to grab objects. It can auto-calibrate the thresholds, so it's much more reliable. And overall, we have a good stepping stone, but there's definitely still a lot more work to be done. Some of this work that we need to work on is we're currently trying to make the signal processing digital instead. So by that, we will eliminate an extra mechanical component. Our design team is also still working on improving the hand further by making it even lighter and improving the grip strength. We're also working on interfacing the 2 different systems more efficiently so that it works even better together. And by continuously working on all of this, we hope that in the near future we'll be able to reach our ideal goal of donating this to a child in need.
Yeah, thank you very much for listening. Any questions?